Ladies and gentlemen, in my work I try to find some new nice approach how to solve one particular mathematical problem, namely let us consider infinite sequence of squares which cites a positive integer, and now we take reciprocals of their areas and sum them up to infinity, and the result what we get is somewhat very surprising, is pi squared divided by 6, so this is what we want to prove, and then further generalize this result, so our proof would work for any even positive integer exponent at k except of just 2. I try to invent the proof so we would not necessarily need to depend on some very strong mathematical formulas like Weierstrass product formula or complex analysis. There are several other proofs, and I aimed, of course, to compare my own to them, and they always had the one particular disadvantage, namely they needed to depend on some strong mathematical theorem, or either they couldn't be further generalized to the formula I mentioned. So in the theoretical part of my paper, I present a gamma function which is crucial part to our solution. Gamma function has some very nice properties, and the most complicated one to prove was the reflection formula. That is the functional equation gamma of x times gamma of 1 minus x is equal to pi divided by sine of px, and it doesn't seem that hard, but it is very hard. My first approach relied on complex analysis, but complex analysis isn't that much intuitive, and it is like it is more different part of mathematics than we are dealing with in the other parts of paper, and to do the proof absolutely rigorously, we need to present very many of formulas and definitions which are not hard to prove, but they are not neither intuitively obvious. So then in order to make the paper wall, we would need to sacrifice some obětovat jako we will need to give some space to complex analysis in addition, which is not that much interesting. It is not new, and if we wouldn't do it, then we would have proof which would have so many formulas, theorems and definitions on which we would need to give a reference, and that is not something I wanted to do. So I, instead of going through Fubini's theorem and some easy substitution, I went with Fubini theorem and then 4 subsequent substitutions which gave us the integral of improper integral of ratio of two polynomials, which we can, and that is the most tricky part and the most inventive one about this proof, is that we can just factorize it, like this is fundamental theorem of algebra, that every polynomial has maximum number of roots, that is its degree, so we, and these polynomials, even if they don't have real roots, they can have complex roots, so it's okay. And we factorize each term on the numerator and denominator, and then tried to convert this product to sum. It's sum, I think, it's sum of arithmetic or geometric series, and to obtain this result there are some further, not easy, but we don't need practically anything after this trick. It's the proof itself only relies on Fourier's theorem and some substitutions. So after that we define psi functions, which is defined as logarithmic derivative of gamma function, and if we proved reflection formula already, we have the hard part done, and these few other formulas, namely recurrence and reflection formula for psi functions, are easy to prove from definition, and we can use them to find some nice other properties, as the representation of difference of psi functions as an infinite sum. And we can come from the reflection formula, we can find some nice infinite sum for cotangent functions, tangent function, which differs from Laurent expansion, and by taking a limit with one parameter goes to 0, we can see that it equals exactly the sum of reciprocals of squares which we wanted, and the psi functions killed each other on the other side as we wanted, so we have nothing more than some elemental functions, and it is very easy limit. It's just using the fact that sine function is asymptotically equal to x, as x is small, so, and then use one L'Hopital rule, and that's it. And then we present the sequence of Bernoulli numbers, which are, I try to use the easiest definition, which is when you consider the sum of powers, then you can write it down as a polynomial with degree n, and it's the linear coefficient of these polynomials. These Bernoulli numbers are linear coefficients of these polynomials, so by taking a derivative and using some clever exponential formulas for cotangent, it is not hard to get generating function, and from that generating function we can use the formula for cotangent we derived from psi functions earlier, and then the result is immediate. So there are some applications. These values are can be found in physics, for example, in deriving Stefan-Boltzmann law, where we can use some reciprocals of fourth powers, and then if you choose randomly two positive integers among the infinite number of them, that this probability that they are coprime is 6 divided by pi squared. It's reciprocal of that sum. And more generally, if you take 3 or n such a numbers, then the probability is 1 divided by sum of mth power, so at k. So